Okay, so today we are covering Chapter 5 and part of Chapter 6, okay? So Chapter 5 is all about sampling distributions, okay? So here's the big idea behind sampling distributions, okay? Let's say I start off, so we're going back to this notion that when we study, the reason why we study statistics is we want to know about our population, but it's too big to study, so we're just going to take a tiny little piece out of this population, okay, and we're going to take a look at this. And this piece that we pull out, this is called our sample, okay? And so let's say from this sample we get some value y bar, the mean of our sample. Okay, the mean of our sample is y bar, okay, and we will say our sample is of size n, okay, sample size n. Okay. And so we always want to know, well, how good is our sample mean y bar? How good of an estimate is it of the population mean mu, right? So what we want to, we wish to know mu, the mean of the population. Okay, but we only get to observe y bar. Okay, and so we're hoping y bar is a pretty good estimate of mu. Okay. But we don't really know, okay? So there's something we can do called a meta study, okay? And we can say, well, hey, if somebody else took a sample, all right? If somebody else took a sample, right, out of this population, so this is going to be sample 2, they would get y bar 2, okay? And we're going to use the same sample size. Same size. So we're going to still take the sample of size n, and we can see, well, how different is y bar 1 from y bar 2, okay? And we can strengthen this, right? We can take another one, okay, and we can do sample 3, okay, and then we would get y bar 3, okay, and we do this more and more and more and more times, okay? So each time we're getting different samples, and every single time we're going to keep track of all the y bars that we observe, okay? So we can call this a meta study. All right, so we just repeatedly take samples of size n from the population. Okay, with each sample, we will record y bar. Okay, so with each sample, we'll record y bar, and then so after thousands of samples, okay, so let's take thousands of these samples. Thousands of samples, okay, and thus, thus thousands of y bars. Okay, let me just pause here. Okay, so we're going to take thousands of these and thus thousands of y bars, okay, and so now that I've got lots of y bars, I'm going to make a histogram or a distribution. I want to study the distribution of y bars, okay? And I wish Okay, I want to study the distribution of y bars. And by being able to study the distribution of y bars, I can get an idea of how good or how close we can expect y bar to be to the mean, right? Like if the distribution of y bars are very close to the population mean, I know that anytime I draw a y bar, it's got to be pretty close to the population mean. On the other hand, if my y bars are all spread out, then I know, oh, if I just take a random sample, it doesn't give me that much information about the population mean, about mu. Okay, does that kind of make sense? All right, and so here's a question for you. What do you think the distribution of y bar will look like? And when I say, what do you think it'll look like, think about, what do you think the center of this distribution will be? What do you think the spread of this distribution will be? And what do you think the shape of the distribution will be? All right, let's here. We've got a little app for this. Okay. Let me do. Is this not it? Is this it? Okay. Okay. So here, this thing up here represents our population. Okay. So our population is normally distributed. And here it says we have a mean of 16. Let me see if I can blow this up. Okay. We have a mean of 16 and a standard deviation of 5. That's what this thing says. Okay. And so I'm going to take a sample of 10 observations here. Okay. And so I'm going to just take one sample. And so here it says we drew some people at random. Okay. These are the 10 people that we got, and it calculates the mean of these 10 randomly selected people, and it says, oh, the mean of these 10 random people is right here. Okay, and we can do this again. 10 random people, and it says the mean of these 10 random people right here. Okay, and I'll do this again. Da, 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 da. Okay. And got the mean over here is over here. All right, so I can do this. We can just have the computer do like 5 at a time. And so we're going to just start drawing a bunch. So here's 5. After 123 samples, it looks kind of like this. And so I'm just going to say, hey, give me. This is after 20,000. So we've done this 20,000 times. And what does this look like? It's unimodal and symmetric, right? And what is the what's the mean of these things? It's the same as the mean of the population, and that's expected, right? So we can ask, what 10 if we're taking 10 people at random out of here, okay, we're expecting the mean of those 10 people to be close to the population mean, okay? And so we're getting centered here. What's this spread like, though?
Narrow.
Yeah, there's less spread here. There's less spread, okay? What do you think would happen if instead of taking samples of size 10, I took samples of size 20? Do you think we would get more spread or less spread in our sampling distribution? So wait, let me go back in time, and so this is, so my standard deviation here is like 1.59 here, okay? So if I take samples of size 20, do you think my sampling distribution will have more spread or less spread? Okay, well, let's see what happens, all right? So write this down. Or with n equal to 10, okay? So write population mean 16, standard deviation 5. with n equal to 10, the sampling distribution has a mean of 16 and spread of 1.59. Okay, so I'm going to take samples of size 20. So the spread was 1.59 when we had samples of size 10. Okay, so let's look. Let's just animate one and just kind of get an idea here. So I'm drawing 20 people now. So it takes a little bit longer to animate our 20 people. Okay, we're going to get another 20 people. Okay, so you know, so far it's like, okay, well, you know, we're just getting a few points here and there. What's this thing gonna look like? Okay, well, let's just do like 10,000 here. Okay, does it look different? Just a tiny bit. What do we see? It's calculated the standard deviation for us. What's our standard deviation? It's like 1.12. So that's smaller. Okay, that's smaller. What do you think would happen if I took samples of only 2 at a time? Spread would increase, right? So I get 2. So here, when I'm just drawing only 2 people, it's very possible for 2 people to end up out here, and I get a sample with a mean out here. I'm drawing 2, and I get a sample mean out here. Okay, so let's so we'll crank this up, and okay, so with samples of just size 2, I'm getting a standard deviation of 3.55. Okay, all of these have a mean of around 16. Yes.
Is there like an easy explanation as to why that is? I thought with a bigger sample you have a better chance of getting a more diverse database.
Yeah. Okay, so this is the distinction. You're absolutely right. When you take a larger sample, the individuals in that sample are more likely to be different from each other. Or I shouldn't say more likely to be different, but just each sample will probably have a bigger spread, okay? Each sample. But our sampling distribution is not the distribution of samples. It's the distribution of sample means. So you've got 20 people, and you're boiling those 20 people down to a single number, the mean of those 20 people. Okay, and then we're keeping track of those sample means. Okay, so when you take 20 people, you might get some unusual people, right? If you get 100 people, you're going to get a few weirdos in there, right? You're going to get some extreme people, whether it's high scoring or low scoring or whatever. You're going to get some extreme people, you know, when you take a sample of 100 or something like that. But if you average all of those people, that's very likely to be close to the population mean. Okay, so when you take 20 people, okay, you might get a few strange observations, but you know, maybe you get 3 strange observations, but there's 17 other people to kind of average those things out. Okay, if you're taking only samples of 2, it's possible for both of them to be kind of on the high side, or both of them to be kind of on the low side. Okay, now chances are you get 1 high and 1 low that kind of balance out, but it's also very possible to get 2 high or 2 low or something like that. When you take samples of size 10, you're going to get some of this balancing out business happening, but not as much as when you get samples of size 20. And so when you look at each individual sample, yes, you're going to have more spread in the individual sample of 20, but we're not keeping track of that. We're keeping track of the sample mean. And so when we're only keeping track of the sample mean, we're boiling down 20 to a single number. What happens is the larger sample has more, you know, kind of this evening out thing going on, okay? And so the sample, when we keep track of the sample means, the distribution of sample means for a sample of size 20 is quite small, okay? And then with smaller samples, we get a little bit more spread, okay? And you know, the smaller our samples go, we get more and more spread. Okay, does that make sense? Okay, so that was with a normal population. So let me just kind of summarize what we observed, okay? So with a normal population, Okay, we took samples, took many samples with the computer, and you know, we kept track of the sample means. Okay. And what we observed was that the sampling distribution was unimodal and symmetric, you know, kind of like the normal, like a normal distribution. Okay, the mean of the sampling distribution was the same as the mean of the population. Okay, and the standard deviation of the sampling distribution was what? Less than the sampling standard deviation of the population. And what else did we see? With larger samples, what happened to the spread of the sampling distribution? Okay, with larger samples, the standard deviation of the sampling distribution got smaller. Okay, so here's the question. What do you think will happen if the population was not normal? So here our population was unimodal and symmetric, and our sampling distribution ended up unimodal and symmetric. Okay, so our population was normally distributed. What do you think will happen if the population's not? So what if my population is uniform? Do you guys have all of this written down yet? Okay, I'll give you another second. Okay. So here I'm going to change this from normal to uniform, okay? So what this means is that all numbers, so here we're just drawing a sample, the range of values goes from 0 to 32, okay? And let's see what happens, okay? So here I can draw samples of 2, and I get a mean here, another sample of 2, and then okay. All right, let's see what happens here, okay? What do you think, you know, if I do this thousands of times, what do you think are the distribution of sample means? Here I'm taking only 2 samples at a time, okay? So this is like rolling 2 32-sided dice, okay? I'm rolling a die that goes from 0 to 32. They all have an equal chance of showing up, and I'm rolling 2 of them. Okay? What do you think this thing will look like? No takers, huh? Okay, well, let's see what happens. I'm going to just do... This black bar represents how likely this number is to show up, okay? And so 32 has this probability of showing up, 16 has this probability of showing up, 0 has this probability of showing up, okay? So all of the numbers have an equal chance of showing up. So it's flat. It's like rolling a die. All of the numbers have an equal chance of showing up, okay? Whereas when I had a normal, the numbers close to the middle are more likely to show up. The numbers out here are unlikely to show up, right? Okay? That's what we're saying here, okay? So here, you know, I'm just drawing 2 numbers at a time. What's this thing going to look like? Okay, I'm just going to jump straight to it. we'll just do 100,000, and we get this pyramid-looking thing. Is this surprising? Is this weird? Kinda. All right. So just think of this. This is like a 32-sided die. Okay. Think about just two dice distribution. Let me look at this. Okay. So here we go. Can I blow this up here? View image. This is the exact image that I want. Okay, this is much smaller than what I wanted. Okay, so here we are showing, you know, how many ways can you get the number 2 when you roll 2 6-sided dice? There's only one way, right? How many ways can you get 12? There's only one way. How many ways can you get 11? There's 2 ways to get it. How many ways can you get 10? There's 3 ways, okay? And with 7, there are 6 ways to do it. And so we get this pyramid shape, okay? And this is just an extension of that. Now we got 32-sided dice. So this is effectively, how many ways are there to get 64, or basically where your average is 32? There's only one way to do it, okay? All right, that's with a sample of size 2. Let's take a slightly bigger sample of size 5. So now we're going to roll the die 5 times and take the average, see what happens, okay? What do you think is going to happen here? Are we going to get a pyramid? Are we going to? So actually, we don't get a pyramid anymore. We get a little hill. Okay. What's going on? What's going on? Okay. I'm gonna so I should have shown you the standard deviation. So the standard deviation here was 6.73. The standard deviation up here is 9.52. Okay. Population has a standard deviation 9.52. With 2, I get a smaller standard deviation 6.73. Okay. Here I'm going to take 5. We're getting kind of a hill-looking thing, okay? We're going to take samples of size 10. What do you think is going to look? Okay? Also a hill, okay? In a smaller standard deviation. And then I'll just jump up to samples of size 20. And this it's very much like the normal distribution, okay? Or it actually is the normal distribution at this point, okay? So with the uniform, we ended up getting a normal distribution looking thing, okay? And so I'll explain all of this. Well, okay, so think about this, all right? Let's say we're rolling, you know, how are we getting this thing now, okay? How are we getting this hill looking thing, okay? So now we're rolling 5 dice, okay? They all have an equal chance. Now the only way to there's only one way to get an average of 32, and that's for all 5 dice to roll 32, and that's quite unlikely to happen, okay? There are now several ways to get kind of this central number, okay? You can have one dice that's high, one dice that's very low, you know, another dice, you know, some in the middle and something like that. And so it's quite likely to get something near the middle. And it's also, if one of those dice is just off by 1 or something, it's not going to throw you way out here. It's just going to throw you off just by a little bit, okay? And so there's quite a few ways for your average. Now that you're throwing 5 dice, it's quite a few ways to get an average of 16. There's also quite a few ways to get an average of 16.2 or 16.4, something close to 16 but not exactly that, okay? And so we're seeing this type of thing going on. And then so with the more and more dice you throw, in this case, it's quite possible to get things that are very close to the middle and also just ever so slightly off from the center. And so we end up getting a normal distribution here. Okay, so that was, you know, the normal, which is symmetric, and the uniform distribution, which is also symmetric, okay? It's not unimodal, but it's also symmetric. What would happen if I have a skewed distribution? So this is unimodal, but it's skewed. This has a mean of 8, okay? This blue right here represents our mean. This spot right here represents our median, okay? And the standard deviation is quite high at 6.22, right? What do you think will happen when I take samples and we're looking at the distribution of sample means? Okay, so we'll take 2 samples of 2 at a time. All right, and so I'm going to just crank this up. Okay, and yeah, we get a skewed distribution here. Okay. What happens as I take larger and larger samples? So the spread's going to shrink. What about the skew? Will that remain or will that go away? Let's take a look. So this is with samples of 2. You can crank this up to 5. Okay, and this is what I'm getting. Okay. There is an actual, we haven't talked about this, but there is a way to actually measure the skew. And so here the skew has gone from 0.83 to even smaller, so we are getting, kind of less skew observed here. And when you look at it, it only looks ever so slightly skewed, right? It only looks like a tiny bit skewed. With samples of size 10, you know what's going to happen? Is it skewed? Maybe just a tiny bit. Just a tiny bit, right? With samples of size 10. Okay, we'll jump up to samples of size 20. Is this skewed? There is just a tiny piece, a little bit more over here than over here. But at this point, I would say it's not even worth mentioning that it's skewed, okay? Like it's, the amount of skew that we're experiencing here is practically negligible, okay? Yeah, the skew is not 0, but it's quite tiny, okay? And at samples of 25, there's hardly any skew to even mention, okay? This bar is ever so slightly taller than this one, but if you saw this by itself and you didn't see this top part up here, you would not say that this is skewed. You would just say unimodal symmetric, right? And so, yeah, because our parent population has skew, maybe there's traces of it left, okay? But what we see is that it's unimodal symmetric. It fits the normal model quite well. Okay. All right. Here's the last one that I'm going to show you. Okay. Okay. So this we would say is what? Bimodal, right? Let's So we've got bimodal distribution here. What do you think our thing's going to look like? Do you think we'll get unimodal, bimodal? Yeah, let's see what happens. Okay, so our mean is 13.59. I'll start off with a sample size of 2. Okay, and so here, in both of these cases, we're getting things. I want to just show you. I want to see something. Okay. All right, let's just crank this up here. This is with samples of 2. What's going on here? Yeah, we're getting trimodal. So this is kind of the peak where both numbers came from this peak. This is the peak where both numbers came from this peak. And then this one is where one came from this side and one came from over here. Okay? So that's why this one's taller, because this one's like, one comes over here, one comes over here. One, this is both coming from over here and both coming from over here. That's with samples of size 2. Samples of size 5, let's see what happens. Okay, So this is, we're losing some of this, but this is like with samples of size 5, this is where 3 have come over from over here and 2 have come over here, and so we're getting a peak here. And this is where 3 have come from over here and 2 have come from over here. Okay, and we're getting, you know, there, you can imagine little hills, and so they kind of overlap, but we're getting a dip here. Okay, and we get this kind of funny shape. This is like kind of 4 and 1, and this is like 5, and this is 4 and 1 and 5. Okay, with 10, look at that. We it's kind of balanced itself out, and with 16, we're getting something like this. And then, you know, at n equal to 20, it's practically unimodal and symmetric. This looks like the normal distribution here. Okay, so what does all of this say? All of this says is that this was with a normal population, okay? And we can say even with non-normal populations, what happened? What happened was all of our sampling distributions, the mean of the sampling distribution was the mean of the population, okay? And what we also saw, the standard deviation of the sampling distribution decreased as the samples got larger. Okay, and what can we say about the shape of all of these sampling distributions? They became unimodal and symmetric as long as what?
The sample size was large enough.
As long as our sample size was large enough. So when our sample size was only 2 or 5, they weren't really unimodal and symmetric, okay? But when the sample size started reaching 20, 25, then they all became unimodal and symmetric, okay? So with non-normal populations, the shape became unimodal and symmetric. As the sample size, or when the sample size became quote-unquote large enough. Okay, and so this is, we call this the sampling distribution of y bar, and it is defined by what we call the central limit theorem. Okay, so do you guys have all this written down? All right, so we've got the central limit theorem. And what we're talking about is we're talking about the sampling distribution of y bar. Okay, so, and what the central limit theorem says is that the sampling distribution of y bar will follow a normal distribution. Okay, so this is a step beyond just saying unimodal and symmetric. We're saying it's going to follow the normal distribution, okay? The mean of the sampling distribution is equal to mu, which is population mean. Okay. The standard deviation of the sampling distribution. Okay. And another name for the standard deviation of the sampling distribution, this is sometimes called the standard error. Okay, is equal to sigma, this population standard deviation, divided by the square root of n. Okay, so this is population standard deviation divided by square root of the sample size. Okay, and so this captures the notion that when our sample size increases, as n gets bigger, our standard error, or the standard deviation of the sampling distribution, will decrease, right? Because this is in our denominator. Okay. So it's going to follow normal distribution, okay, as long as the sample size is large enough. Okay. So I'm going to just present this to you as a fact, okay? And well, and it's true, okay? But this is not a mathematical statistics class, so I'm not going to try to prove this to you, okay? So I'm just going to say, hey, you kind of saw it happening with the computer simulations. We saw it became unimodal and symmetric. I'm not going to try to prove to you that it's actually a normal distribution and that it has all of these properties, okay? If you're interested in that kind of stuff, you can take a course on mathematical statistics, or you can read on Wikipedia about the central limit theorem, and it'll go into the explanation of the proof. But you know, the scope of this course, I'm just going to say, hey, this is what happens. This is what you need to know. Okay. So here's this thing. What is the notion of large enough? Okay. So what is large enough? Large enough will be defined as large enough. We have just a vague definition here. Okay. So large enough. Okay. If the population is normal, is normally distributed. Okay. Any sample size is large enough. Okay. You can take samples of size 2, and the sampling distribution of y bar will follow a normal distribution with mean mu and standard deviation sigma over the square root of 2. Okay? So you can take tiny samples, and this property will hold. Okay? If the population is unimodal and symmetric, you just need a slightly bigger sample. Okay? Small samples, which is ill-defined, but probably, you know, samples of, I guess, you know, how unimodal and symmetric. It's basically, if it looks a lot like the normal distribution, you can get away with really small samples. If it doesn't look like the unimodal, if it doesn't look like the normal distribution, you need bigger samples, okay? So if the population is not normal, I'll just say if the population is not normal, you need a bigger sample. Okay, and the rule of thumb is that n greater than or equal to 25 is big enough for most situations. Okay, but if you've got a really skewed distribution, okay, something like income, okay, where, you know, most people are between, you know, 30 and 100,000 a year or something like that, okay, but you've got people making $1 million a year or $5 million a year or something like that. So you've got these really skewed things where you've got people making, you know, literally 100 times or 1,000 times more than other people, okay, then n equal 25 is not going to be big enough, okay? In those cases, you'd probably want to apply some kind of transformation. You'd want to take the logarithm of all of these numbers, which will help bring down some extreme numbers. But if you want to kind of just say, I need a big sample, then you're going to need something really big, like samples of size 1,000 or something, okay? But this is what we've got, okay? So the rule of thumb is n greater than or equal to 25, but if the data is really skewed, or if the population is really skewed, you will need even larger samples. Okay? Is this okay? So this tells us that anytime we're taking a sample, and this is a huge thing. It says, you know, no matter what your population looks like, even if you have no idea what your population looks like, if you're taking big enough samples, we know that the mean of that sample, y bar, so the sampling distribution of y naught bar, we know that y bar will follow a normal distribution, okay? Which is a rather remarkable conclusion, because we don't know what the population looks like, but we do know that y bar will follow a normal distribution, and we know that that y bar is centered around the population mean, and that its standard the standard deviation isn't going to be that the sampling distribution of y bar has this standard deviation. Okay, so let's try an example problem using this. Okay. Okay, so let's say. Okay, so we are looking at seeds. Okay, so we're looking at princess bean seeds, which I don't know anything about, but apparently, okay, what is a princess bean? I'm gonna look this up. Okay, so the princess bean seed, okay, comes from, okay, so princess bean seeds. All right, the weight of a princess bean seed follow the normal distribution. Okay, the mean weight is 500 milligrams, and the standard deviation, because it's a population, I should say sigma, is 120 milligrams. Okay, so I'm going to put down two questions. A, if we randomly select a seed, what is the probability that it weighs more than 600 milligrams? Okay, so that's part A. And then part B, if we randomly select 9 seeds, okay, what is the probability that the mean weight of these 9 seeds is over 600 milligrams? Okay, so go ahead and take a few minutes and answer these questions here. Okay, and then we'll go over the answers. And again, if you are on YouTube and you'd like to do this, pause the video, because I'm going to pause it right now. All right, so Part A, I'm hoping was okay. This is a normal problem. This is the type of problem we saw, you should have seen last week in your homework with the normal distribution. So all this is doing is we're saying, hey, we are centered at where? 500. I'm drawing a line at 600. What's the area to the right? Okay. So what's the step I'm taking next? I would say Z is equal to what? 600 minus 500 divided by 120, and I get 0.83. Is this okay with everybody? Yeah? Okay, so I get 0.83. I then look this up in my Z table. And so I could look up the area to the left of 0.83, or I can look up the area to the right of negative 0.83. Okay? So I'm just going to go to negative 0.83, and I get 0.2033. Okay, so this area is 0.2033. Okay. Are we okay with part A? Okay, so that's good. Okay, so with part B, here's the key. It says we randomly select 9 seeds. So now we are dealing with a sample of 9 seeds. And here we're asking, what is the probability that the mean weight of these 9 seeds? So this tells us the mean weight of our sample. We are now interested in a sampling distribution. Okay, so here we have a sampling distribution. Okay. And from the central limit theorem, what do we know? We know the sampling distribution has what shape? It's a normal distribution, right? The sampling distribution is normal. Okay. And what is what's that? That's just what we've said as fact. From the central limit theorem, we said the sampling distribution of y bar, meaning the sampling distribution of the mean weight of a sample, right? Y bar is the mean weight of a sample, so we're looking at the mean weight of y bar of these 9 seeds, okay? And we know that the sampling distribution follows a normal distribution. What's the mean of that sampling distribution? Mu, same as the population mean. What's the standard deviation of our sampling distribution? Sigma over the square root of n, okay? So the mean is equal to what? 500, and our standard deviation is going to be sigma over the square root of n, so this is going to be what? What's my number up here? 120 divided by the square root of n, and I'm taking a sample of 9 seeds, right? So the square root of 9, so I'm going to do 120 divided by 3. My standard deviation is 40. Okay, so at this point, then it becomes just a regular old normal model problem. Okay, the key here is recognizing that we're asking about the mean weight of a sample, so we're dealing with the sampling distribution of y bar. Okay, so I'm centered at 500. My cutoff is still 600. Okay. But what happens to my z? My z is now going to be 600 minus 500, and I'm dividing not by 120, but I'm dividing by 40. Okay? So my z ends up being 2.5. Okay? So this is a dramatic difference, right? Because we said z's greater than 2 are unusual, whereas here we got a z less than 1, which is quite normal or mundane. Okay, so we look up z equal to 2.5, and we want to know what's the area to the right of z equal to 2.5. I'm just going to look up the area to the left of negative 2.5, but you could look up the area to the right or to the left of positive 2.5 and subtract that from 1. And I look this up and I get 0.0062. okay? And so my answer here is 0.0062. So when you're taking one seed at random, it's quite a regular occurrence for that one seed to weigh over 600 milligrams, okay? It's not a big deal. It happens about 20% of the time. 1 in 5 seeds weigh over 600 milligrams, okay? But when we're taking a sample of 9 seeds, for 9 seeds, for the average of those 9 seeds to be over 600 milligrams, suddenly that's a very strange occurrence. That happens less than 1% of the time, 0.0062, okay? All right, so study this example. You'll definitely see something like this on the quiz, okay, next week, and so we've got that. Are there any questions on this? Do we feel okay? Do we need another example, or are we okay on this? You're okay. All right, great. Then we'll stop here. We'll take a break, and then we'll come back and we'll start getting into chapter 6.